Alright, in this video we study how to integrate rational functions. A rational function is a ratio between two polynomial functions, and we apply a technique called partial fraction decomposition to simplify a rational function. And this technique involves a bit tedious calculations, but anyway, we have to deal with it. Okay, let's start. First, let's review what a polynomial function was. Okay, polynomial function is something like this. Let's say f of x is equal to an. An is a real number times x to the power of n, an minus 1, x to the power of n minus 1, and so on, and a1x plus a0x. So all these coefficients, a1, a2, a0, whatever, they are all real numbers here. Okay, so k is from 0, 1 up to n. And if we integrate this function, so if we integrate this f of x with respect to x, we get, what do we get? 1 over n plus 1, an x to the power of n plus 1, plus 1 over n, an minus 1, x to the power of n, and so on, and 1 over 2, a1x squared plus a0x plus constant. So as we can see, the integral of a polynomial function is again a polynomial function. And let's say if we have two polynomial functions, f of x and g of x, so these are polynomial. And if we take the ratio of these functions, this is called a rational function. So as it turns out, if we integrate this function, if we can ever integrate it, this may not be a rational function actually. So sometimes it involves logarithm, sometimes it involves inverse trigonometric functions. Yeah, of course it can be a polynomial function or rational functions, but it's not necessarily a rational function. To integrate a rational function, we use a lemma called partial fraction decomposition. That means we decompose a rational function into partial fractions. But before stating this lemma, let us see a few examples. Okay, first example is this. Suppose we have this function f of x that is x plus 5 over x squared plus x minus 2. So this is a rational function, and we can factorize the denominator as x, let's see, minus 1 times x plus 2, right? And this rational function can be decomposed into two parts. That is some constant over x minus 1 plus some constant over x plus 2. So the denominators here and here are the factors of this denominator in the original rational functions. So how do we find a and b? So we are assuming that this is equal to this. So let's equate them as this, x minus 1, x plus 2, and consider this equation. Okay, so let's multiply both sides by this product. Okay, so on the left hand side we have, so this x minus 1 will be cancelled, and we have x plus 2, and here we have b times x minus 1, which is equal to x plus 5. So if we put x equal to, let's say, negative 2, then this will be 0, so it's gone. And from here we have negative, let's say, negative 3b, and here we have 3. So that means b should be negative 1. And if we put x equal to 1, then this factor will be 0. So we have here a times 3 is equal to 1 plus 5 is 6, so a is equal to 2. So therefore, we have x plus 5, x minus 1, x plus 2. So this can be decomposed into partial fractions as, so a is 2 over x minus 1 minus 1 over x plus 2. So this is simplified. So if we want to integrate this function, then we can just integrate these partial fractions, and which is a lot easier. And of course, this should be 2 times log of absolute value of x minus 1 and minus log of x plus 2 absolute value. And of course, you can put them together as log of x minus 1 over x plus 2 and everything in absolute value. And don't forget constant. And that's it. As we remarked earlier, the integral of a rational function may not be a rational function. Indeed, in this case, it's a logarithmic function. Okay, next example is a little bit more complicated. So f of x, let f of x be x to the power 5 minus x to the power 4 plus 3x cubed minus 3x squared minus x minus 2 over x to the power 4, x minus x cubed minus x plus 1. So since the degree of the numerator is higher than the degree of the denominator, first we want to take a polynomial out of the numerator. Okay, so for that we do a long division, for example. So let's do that. x5 minus x4, 3x cubed minus 3x squared minus x minus 2. So let's do a long division. So x4, this is x5, 4, and negative x squared plus x. So minus, so this is gone, 3x cubed minus 2x squared minus 2x minus 2. So that's it. So f of x is x plus 3x cubed minus 2x squared minus 2x minus 2 over this thing. But this one can be factorized. Let's factorize that first. So x4 minus x cubed minus x plus 1. So first let's factorize factor x cubed out. That means x minus 1 here, and this one x minus 1. So we have x minus 1, x minus 1, and x minus 1, x cubed minus 1. And we can factorize this again. So that will give us another x minus 1. So that's squared now. And the remaining part is this. And this, if you insist, you can factorize by using complex numbers. But we don't do that because we don't want complex numbers here. Okay, so the denominator becomes this. X squared, x minus 1 squared, x squared plus x plus 1. Now, so this part is easy to integrate, and this part we decompose into partial fractions. So how do we decompose this rational function into partial fractions? So here's how we do it. So we have 3x cubed minus 2x squared minus 2 minus 2 over x1 squared, x squared plus x plus 1. So let's suppose this can be decomposed into this, ax plus b over this thing, Here the denominator is a quadratic form, so the numerator can be a linear form of x. So it's lower degree than the denominator, which is x squared. So we have x here. And for other fractions, we have, let's say, c, some constant over x minus 1, and d, some constant, x minus 1 squared. So let's multiply both sides by this. Okay, then we get 3x cubed minus 2x squared minus 2x here, 2x minus 2, and ax plus bx minus 1 squared, and c times, let's see, x minus 1, x squared plus 1, x plus 1 plus d, and x squared plus x plus 1. Okay, so just substitute some values into x and you will find some simultaneous linear equations involving a, b, c, and d. So there should be 4 equations in order to find these 4 unknowns. For example, if we put x equal to 1, then this and this will be gone. And you have an equation. You can determine the value of c from that. And if we put x equal to 0, then we have some other equation. And if we put x equal to 2, we have some other equation. And if we put x equal to whatever. Actually, for that matter, you can put some imaginary or complex numbers for that, for the sake of determining these unknown parameters a, b, c, d. So it's an exercise to determine the values of a, b, c, d, but let's just do x equal to 1 first, for the sake of demonstrating the process. So if we put x equal to 1, the left-hand side will be, what is it? So 3 minus 2 minus 2 minus 2. So that is, wait a minute, what is it? Negative 3, the left-hand side. And the right-hand side becomes, so this is 0, this is 0. So it's just this term. So d times 1, 1, 1, that's 3. So 3d is equal to negative 3, so therefore d should be negative 1. And next, let's put x equal to 0. Then the left-hand side is 0, 0, 0, and negative 2, and right-hand side is what? So this is 1, and x is 0, so that will be b, and x is 0, so plus c minus 1 and times 1. So that is b minus c. And oh, wait a minute, this one is also there, so I forgot this one. So negative, so d is negative 1. Negative 1 times 1 equals to, what is it? Equals to b minus c minus 1. So this is equal to, so b minus c is equal to negative 1. So we have this equation. And if we put x equal to 2, we have another equation. And if we put x equal to whatever, then we have another equation. And solving all these will give you the values of a, b, c, and d. d is negative 1 already. And the result should be this. So a is 1, and b is 1, and c is 2, and d is negative 1. So you should get this result. So if we know this, then just plug into this, and so a is 1, b is 1, so x plus 1, and c is, what is it, 2, and d is negative 1. So it's negative 1. So we have this partial fraction decomposition. So now let's integrate these parts in turn. Okay, so the easiest one should be this one. Okay, so if we integrate this, x minus 1 dx, that is just log 2 times log x minus 1 plus constant, and that was easy. And the next one next easiest one should be this one. So if we integrate this, 1 over x minus 1 square dx. So this should be, let's see, x minus 1, and we have negative sign here. And if we have a negative sign, okay, so this is it. Plus constant, right? So if we differentiate this, we get this times negative sign, right? So that's it. And for this one, it's a little bit complicated. So we have x plus 1 over x squared plus x plus 1. So how do we integrate this? So if we look at the denominator, we have x squared plus x plus 1. And if we differentiate this, we have 2x plus 1. So if we have this in the numerator, then it's easy to integrate, and we can just use integration by substitution, right? So, for example, if we have 2x plus 1 over x squared plus x plus 1, then the numerator is just the derivative of this one. So that means we have log of x squared plus x plus 1. So that is, just to check if this is indeed the antiderivative of this one, just differentiate this and you should find this as a result. Okay? So let's make this numerator as close as possible to this. Okay? So that is, so let's do it. X plus 1, x squared, x plus 1 dx. So first let's multiply by 2 and divide by 2. Okay? So now we have 2x plus 2 over x squared plus x plus 1. But we want 2x plus 1, so we can split this 2 into 1 plus 1. Okay, so we have 1 over 2, 2x plus 1 over x squared plus x plus 1 dx, plus 1 over 2, and 1 over x squared plus x plus 1 dx. So this part, we already know the answer. So that is 1 over 2 log of x squared plus x plus 1. So what about this second integral? But before that, by the way, I didn't write absolute value here, but I just wrote parentheses. Why is that? Can this be negative? Actually, no, because the discriminant of this quadratic form is always negative. So this is 1 times x squared plus 1 times x plus 1. So the discriminant of this will be 1 squared minus 4 times 1 plus 1, which is negative 3. So that means, it's obvious if you plot this function, it will be above the x-axis. So it's always positive. So we don't have to worry about the absolute value. It's always positive, as long as x is real number. Okay, so next, this. So how do we do that? Okay, in order to compute this integral, first we need to complete the square of this denominator. Okay, so x squared plus x plus 1 is, let's complete the square here. So that should be, let's see, x plus 1 over 2 and squared minus plus 3 over 4, right? So let's write this as this. So factor this 3 over 4 out, and we have 4 over 3 x plus 1 over 2 squared plus 1. Okay, now let's suppose, for example, z equals to square root of this thing. Okay, so let's see. 2 over square root of 3 and x plus 1 over 2. So let's change the variable here. So from this we have dz is equal to 2 over square root of 3 dx. And using this substitution, we can integrate this function, x squared plus x plus 1 dx becomes this. So first we completed the square like this, and substitute this. We have, let's see, so 1 over 3 over 4, and we have z squared plus 1, and dx from here, dx becomes square root of 3 over 2 dz. So we have square root of 3 over 2 dz here. Okay, so let's see. So we have this 4 here, and this is cancelled. So we have 2 square root of 3 over 3, and this integral. But this one is arctangent. So we have this arctan z. And if we put back this substitution, arctan this. So what is it? 2 over square root of 3 x plus 1 over 2. So this should be it. So again, the integral of this rational function here becomes a non-rational function, but it's an inverse trigonometric function. Okay, so now let us state the lemma of partial fraction decomposition more formally. So here it is. Any rational function can be decomposed into one of the following 3 forms. Decomposed into the following forms. So first, polynomial. And this happens if the numerator has a higher degree than the denominator. And second, something of this form, constant divided by x plus constant to the power of some natural number. Okay, and k and a here are real numbers, and m is a natural number. Okay, and third, something of this form, ex plus d divided by x squared plus bx plus c to the power of m, where b, c, e, d are real numbers, and m is a natural number. And furthermore, we have the discriminant of this quadratic form must be negative. That is, b squared minus 4c is negative. So this condition means that this quadratic form cannot be decomposed into simpler forms, such as x minus a times x minus b, as long as we impose the condition that this a and b must be real numbers. Okay, so the roots of this quadratic form are imaginary or complex, not real. So any rational function can be decomposed into the finite sum of either polynomials or of this form or of this form. Okay. Now we know how to integrate polynomials, and let's consider how to integrate the functions of this form in general next. Okay, so for this integral k over x plus a to the power of m, we consider two different scenarios. So first one, when m is equal to 1, so this exponent here is equal to 1, then we have this integral. And it's easy to integrate this, and we have k times log of the absolute value of x plus a plus constant. And second case, when m is greater than 1. In this case, x plus a to the power of m dx is, so it's easy to integrate, and we have, let's see, what is it? It should be x plus a to the power of m minus 1 and times negative 1 over m minus 1. So let's simplify a little bit. So that should be negative m minus 1 x plus a to the power of m minus 1 plus constant. Okay, next let's consider the integral of this function, ex plus d over x squared plus bx plus c to the power of m. Okay, for this one, we first complete the square of this part. Okay, so let's do that. X squared plus bx plus c, so that is x plus b over 2 squared plus c minus b squared over 4. Okay, but be careful that we have a condition that b squared minus 4c is negative. Okay, so that means this part, so c minus b squared minus 4 is 4c minus b squared. This is always positive, right? So let's put, since it's positive, let's substitute this as h squared. So we have x plus b over 2 squared plus h squared. Okay. And from here, let's factorize this h squared. H squared, and we have h squared x, wait a minute, it's 1 over h squared and b over 2 squared plus 1. Okay, now let's substitute z equals to x plus b over 2 over h. Okay, so let's simplify a little bit. So that will be 2x plus b over 2h. So under this substitution, this equation becomes h squared and z squared plus 1. And moreover, from this substitution, dz is equal to 1 over h dx. So let's modify the original integral using this new variable z. So the original integral was ex plus d over x squared plus bx plus c to the power of m dx. Okay, so this becomes so wait a minute. So x is equal to, let's see, h z minus b over 2. So e h z minus b over 2 and plus d over, so h squared z squared plus 1 everything to the power of m times dx is h dz. Okay, so let's simplify this a bit. So from denominator we have z squared plus 1 to the power of m, and from this h squared we have h squared to the power of m, and for this one we have e h z, new coefficient here, and plus d minus be over 2, and we have h here. Okay, so let's put this and this together, and this and this together, together with this. So let's define a new constant, let's say e prime, z and d prime, over z squared plus 1 to the power of m dz, where e prime is, let's see, so e h squared and divide by h 2m minus 2. And d prime is this one divided by this and multiplied by this. So that is d minus be over 2 over h to the power of 2m minus 1. So new constants here. So we can split this integral into two parts. One is this, z squared plus 1 to the power of m dz, plus d prime and 1 over z squared plus 1 to the power of m dz. And the first one is easier to calculate. So this first integral here, let's calculate this, z squared plus 1 to the power of m dz. And again, we need to consider two cases. When m is equal to 1, then we have this. And if we multiply 2, divide by 2, and we get 1 over 2 log of z squared plus 1, right? And when m is greater than 1, then again we have this to z squared plus 1 to the power of m. That becomes 1 over 2, and let's see, z squared plus 1 m minus 1 over 1, and negative 1 over m minus 1. So that is, let's see, negative 2m minus 1 z squared plus 1 to the power of m minus 1. So that's it, plus constant. And the remaining part, this one, you should be familiar with this already, because we did this integral when we studied integration by parts. So let's put this Im is equal to integral of 1 over z squared plus 1 to the power of m. Okay, then if you remember, I1 is just this, which is arctangent. And for general integral m plus 1, we have this recursive formula. You should try to derive this again on your own. To m here, and im plus, what was it? 1 over 2 m z over z squared plus 1 to the power of m. Right? So we can calculate this integral one by one. So starting from this, then we calculate I2, then I3, and so on. Okay, so we have studied integration of rational functions by using partial fraction decomposition. And now we know how to integrate each of the components after decomposition. And that's all for this video. See you later.